So the fundamental theorem of calculus. Okay, so obviously by the name of the theorem, I think you can imagine that it's very important. So there's two parts to the theorem. Okay, so up until now, what do? We did antiderivatives, then we did Riemann sums, okay, and we use the same symbol for integration. Okay, in both cases we use the same symbol. So now the purpose of this theorem is to show you that finding the antiderivative or finding the area under a curve is pretty much the same thing. Okay, they're related. Okay, you will see the relation between the area and the antiderivative right away. Okay, so there's two parts to the theorem. So fundamental theorem of calculus 1. Okay, so the first part is like this. If f of x is equal to the area from a to x of a certain function t, f of t, dt, then if you do the derivative of this function, you will get f of x. That's the first part. I'm gonna explain what this means in a second. Let me write down the second part. What this says is that if f is, big F is an antiderivative of small f, then the area from A to B of small f of t dt is equal to big F of B minus big F of A. Okay, and this is what we're going to call the definite integral, and we're going to talk about this shortly. Okay, so this one is the one we're going to use the most. Okay, and that's basically what it tells me is that if you want to find the area from A to B under the graph of f, you just need to find the antiderivative, plug in B, plug in A, and minus them. Okay, so it's much, much faster than doing Riemann sums. Okay, up until now, we were just doing Riemann sums for this. Now you could find the antiderivative and minus them. Okay, this is the second part, which we're going to prove after we prove the first one. Okay, this one is much easier to prove than this one. Okay, and any questions so far? I'm going to explain you what this means in a minute, but any questions at least on the second one, which is easier? Okay. What does this mean? Okay, let's understand. You have a function from A, and the function, right, is until a certain, so let's call this, so I don't get mixed up in the variables, t, so let's say until x. So this area here is what I called, this area is what I call big F of x. Right? Because I said big F of x is the area from A to x of the function f. Okay, so obviously this area depends on x. If x is a bit further, the area will be different. If x is a bit smaller, the area will be smaller in this case. Okay? So I'm interested here in the rate of change, the derivative, so the rate of change of the area as a function of x. How does the area increase or decrease when I increase or decrease my x? You understand? That's what this means here. And apparently that's what we're going to show. The rate at which the area increases is exactly equal to the value of the function here. Okay?
The volume of the function?
Excuse me?
Sir, do you mind explaining that again?
Of course, I'm going to explain. It's not easy, and there's a lot of information. I agree. Okay, but did somebody else have a question, or I just
I
read?
was going to ask you the same thing.
Okay, so I'm going to re-explain. What the fundamental theory of calculus part 1 tells us is that if I define big F as the area between a and x under the function, okay, I'm defining this F as this area. Since one of the bounds, one of the endpoints of the interval on which my area is defined is variable, so obviously my area is variable, right? If I go from A to B or to 10, I'm going to get an area. If I go from A to 11, I'm going to get another area. So this area here depends on x. That's why it's a function. So far, so good. Any questions here?
It wouldn't depend on A as well?
No, A is a constant. A is not a variable. Okay, starts at 1. Let's say A is 1. Okay, so A is not moving, it's fixed. Starting from A, I'm going to go increase, I'm going to take an x and find the area from A to x. And x is here, x is here, x is here, x is here. Depending x, I'm going to get a different area. Are you okay with the fact that the area here depends on x? Would anybody would like me to repeat? Anybody want me to repeat? It's important because we're going to build a lot of this on this. Sure?
Sir, I have a question.
Okay.
So just the f of x, so basically it all depends on on x?
Yeah, the area here depends on x. And the function, of course. Depends on what the function is.
So that's the whole fundamental theorem of calculus for 1, is that x is a variable and it depends on x, the function depends on x?
No. What it says is that the rate at which this area increases is exactly equal to the value of the function. Okay? If I
What do you mean by the rate?
Yeah, exactly. If I were to increase here my x, I change it by something here. I increase my x a little bit, while my area also increased. Right?
Yeah.
Okay. So I could do by how much did the area increase divided by how much did the x increase. And that's just a derivative. That's a rate of change of big F. So I'm interested in the rate of change of big F. At what rate does big F increase or change? Okay, that's what I call big F prime. And the big theorem tells me that the rate at which it increases, well, it's equal to the value of the function.
Wait, and how is that a derivative again?
It's a rate of change. This is a delta x, and this here, this little region here is the delta big F, if you want.
Okay.
Right? It's like this is the y, delta y over delta x. Okay? That's big F prime. Okay, so that's what I'm trying to show, that the rate at which the area increases is exactly equal to the value of the function. Okay, and if we say this, well, that's another way of saying that the area is actually the antiderivative of small f. limits, right? If you derive this, you get that. So if you anti-derive this, you get that, of course. So that's why it's so important, because I'm showing that the rate of change of the area is exactly the function. Or the area is the antiderivative of the function.
And we're gonna prove that right now.
Yeah, we're going to prove that right now.
Okay.
So you probably have done this in physics without knowing it. When you did mechanics, you were doing when you had a velocity time graph, right? And you would have to find the displacement. Then you would find the area. Remember this?
Yeah.
Okay. What were you doing? You were doing an integral. You were doing a definite integral without knowing it. Okay. You're finding the area under the curve. Why? Why is the area under the curve of a velocity give you the displacement? Did you ever ask yourself this question? Okay, so you, without knowing it, you were using the fundamental theorem of calculus there. Okay, and same thing, acceleration time graph. If you would find the antiderivative, you would get the velocity. Okay, do you have any questions?
Sir,
Yeah.
what's ft?
Sorry, F?
Yeah, ft dt.
Oh, this here? Where's FT?
Your first equation. The integral of xa
This?
ft. Yeah.
It's F. I use the T instead of X because I use the X here.
Okay.
I don't want to use the same variable. Yeah, I could
Okay.
U whatever. So, fundamental theorem of calculus part 1, proof. So, big F of X, we said, was the area from A to X of small f of t. Okay, in other words, small here, A x t. This is my area here. Let's find f of x plus h. Could you tell me what that is? It would be the area from what to what?
From A to x plus h.
Perfect. A to x plus h, f of t. And it would be an area like this. My region will be y, t. So again, my function, and this is a. And now this, instead of being until x, it will be, let's say, until x plus h, a bit further. Okay, it was x. Questions? Okay, so let's now minus the two areas. So let's do f of x plus h.
Sorry,
yeah.
The h is just the extra space that the extra rate that was added.
H, yeah, is just a bit more
Okay.
than x. Yeah, exactly.
Okay.
Can you tell me what that area will be? If I do f of x plus h minus f of x here, if I minus these two areas, what do I get?
Well, h, no? If you remove the x from it.
From x to h?
Sorry?
Change in area?
What is it? From
But
x?
from x to h, right?
X to h? I'm not sure.
Is it the change in area?
So the change in area. So if I draw it like this, it would be, so this area minus this one, I would just get this little piece here, right? Okay, so it will be x plus h So it would be just this area. Do you agree with this? Any questions on what I just drew?
So what's the value of that area?
Value?
Yeah,
What do you mean value? Numbers?
because it's from x to x plus h, right? In between x and x plus h.
Yeah.
It doesn't have a value?
Well, it depends on x and x plus h.
Okay.
These are variables. I don't know. Yeah, does that answer your question? I'm not sure.
Yeah, it does.
Okay. So do you who has question on why this area here is this? Okay. How would I represent it here? How would I express it? It's the area under the curve of f of t dt that we agree. From what to what?
From x to x plus h.
Very good. From x to x plus h. All good? Okay. So now,
Sir?
yes, go ahead.
Please, could you re-explain why it is f of x plus h minus f of x?
Why this is that?
Yeah,
Yeah, okay, because this from a to x plus h, the area from a to x plus h is all the way until here. From a until x is from here to here. So if you minus them, if you do this area minus this one, so you just get rid of this part, you're left with the extra one. Do you see it?
thank you, I get it.
Okay, perfect. Okay, so before I continue, I have to be 100% convinced that you guys are okay with this. If not, I repeat. Okay. You sure? You don't want me to repeat one more time? You're okay? All right. So now I'm going to focus all my attention on this little small region, right? Which is from x to x plus h. Of course, h could be as small as I want, okay? So I hope you're realizing that what I'm doing now is I'm finding the delta y, right, for f, the difference in the f with a small increase of x, okay? So I'm slowly building up the derivative, the definition of the derivative, the limit definition of the derivative for big F. Okay. Let me draw this region. Okay, so I'm going to draw it, let's see here. Yeah, I just hope I could fit everything. So, okay. So let's say my function, I don't know what it's like, okay, but between x and let's say x plus h is here. Okay, so I made it a bit curvy just to exaggerate, and you'll see why. So this whole area here is big F of x plus h minus big F of x. Okay, what's that questions on what I just wrote now?
Sir, on top of
Excuse me?
on top of
I can't hear you, I'm sorry.
So is that the y-axis on top? We can see where you're, yeah.
Yeah, that's the y-axis.
Can you like make it a little bit more clear?
You see now?
Okay, yeah.
Any question here? Okay, so now listen carefully. Now there's an important step.
Sir, you just like draw the curve, like you draw the small part bigger.
Exactly. From
Okay.
x to x plus h. Here it is. Good? Okay, now listen carefully. Since small f is continuous over x and x plus h. Okay, so we're just dealing with continuous functions. Okay, then, so you need to remember something from calculus 1 here, is that a function that is continuous over an interval reaches a maximum and a minimum value. You remember this? What does this theorem called? What is it called?
Gravity.
The
Extreme value theorem.
What the?
Extreme value
Very
theorem.
nice. Okay, so then by the, so I'm going to put it in color because it's been a while you haven't heard this one. Extreme value theorem. Let's go like this. Okay. Two things. There exists, I don't know if I can write with symbols. Have you seen this symbol before?
no.
No? Okay. Let's get used to it. Okay. So there exists, let's call this a small m in the interval x plus h, such that I'm gonna write what this means, okay? Such that f of small m, so is the smallest possible value, okay? So it's smaller than or equal to f of x for all x, okay? So there's two new symbols for you guys. So this means there exists and this means for all.
Sir, can you explain the last part, please?
Yeah, I'm going to show it on the graph also. But what I'm just saying is that since f is a continuous function over a closed interval, okay, then we had a theorem in calculus 1 that tells us, right, the extreme value theorem tells us that the function will reach its maximum and will reach its minimum. Okay, you definitely learned it. I know my class learned it, so you probably did. Okay, if it is continuous, then for sure it reaches a max and it reaches its minimum. It cannot be. It can go on forever. It can be an open dot. There's no other way than to reach the max and the minimum. Okay, that's what I'm saying. That's what I'm saying here. And formally, it means that there exists a value. No, I'm going to write it differently. Okay, there exists a C. I'm going to call it C. Okay, there exists a C such that f of C is equal to. Okay, I'm going to just I don't have much space. Is equal to m. Okay, f of C is equal to a certain value m, which is smaller than or equal to f of x. Can you still see? Yeah, you can see. Okay. Okay, so let me, maybe you got confused here. So what happens is that since, let's look at the graph. Since it is continuous over the interval x plus h, then apparently there is a value here, C, such that f of C is equal to small m, which is the smallest possible value that f takes on that interval. This here represents what I just wrote here in the complicated way. Would you like me to repeat this?
Yes, please.
This is
Yes, please.
yeah, this is a tricky part of the proof. Okay, so again, we start over. Okay, I said big f of x was the area from A to x. I said big f of x plus h is the area from A to x plus h. Here are my two areas. I represented them on the graph. Then I minus the two areas. Here's the subtraction. What do I get? If you minus the two areas, I just get this little area. Okay, so this area is the area from x to x plus h of f. Then I zoomed into this area. Here it is. And then I came in with my brilliant idea to use the extreme value theorem, which is what? It tells me that since the function is continuous over an interval, then this theorem tells me that it reaches a maximum value. It reaches a maximum value and it reaches a minimum value. That's it. That's all I'm saying. So since it reaches a minimum, that means that there's for sure some place between x and x plus h, I'm going to call it C, such that f of C is equal to that minimum value. That's all I'm saying. Is this okay or not?
Sorry, I
So
don't
it's
really
a-
understand. Do you mind like explaining like slower, I guess?
Slower. Okay, so step by step. Okay, so this part on the left, you're okay?
Yeah.
This is okay. So now I'm focusing on this little piece. I'm here. Okay. So what I'm saying is that the function f, small f, is continuous. It's continuous. You could draw it without lifting the pen. Okay? Since it's continuous, then the extreme value theorem tells me that this function will have a maximum. It will not go until infinity for sure. There will be a maximum value that it reaches, and there will be a minimum value that it reaches. Is that okay or not? Does this make sense to you?
Yeah, but I'm saying it would go to infinity at the end of the day, since it would continue going.
No, I'm just interested from x to x plus h. After that, I don't care.
Okay, so in our section that we chose, that it's,
Over x plus h.
okay, I get it. Thank you.
Anybody else have a question?
So, sir, all this is saying is that there's a minimum and maximum, and that's it?
That's it. That's all it's saying. And
Okay.
then it attains it. It reaches its max and its min. Okay, so for now, I just wrote that it reaches its min. I'm going to now write also that it reaches its max. Okay?
Okay.
Okay, are you okay? Anybody would like me to re-explain this? I don't mind.
Sure, could you re-explain the part where you spoke about the C and you linked it with the M on the graph?
Yeah. Okay, so another way of saying that it reaches the minimum value, okay, another way of saying that is that to say that there is a certain value M, okay, for which the function can never go lower than that. Okay, there is a value of M, there's a value M that the function reaches, okay, and that is smaller than all the other values that it reaches. If that's the case, then that M is the minimum value of the function. Okay, so formally here, I'm saying that there is a value C between x and x plus h, for which f of C is equal to the smallest value, which is smaller than all f of x's.
Okay, makes sense.
Okay, good?
Yeah.
Okay, so let's do, if you could help me to write the equivalent sentence for the top. Okay, so we're going to call this D. what can I write here? There exists a D in x plus h such that what? Can you help me? Such that what?
F of D is equal to n,
So I'm going to call this big M, okay, for the maximum, which is
which is bigger or equal to fx. Yes.
very nice for all x. Okay, for all x, of course, for all x in my interval. Good. So what I just I'm writing here. So I'm saying that there is a value here D, okay, such that f of D is equal to big M. Do you have any questions? Okay. So the hard part is done. Okay. The most difficult part was this. Now, if you're clear with this, we could reach our conclusion now. Okay, and get to the proof. So let's observe this picture here. Okay, this little graph. Everything's happening here. Well, I'm interested in this area. I'm gonna put it in here. I'm interested in this area here. Right? Don't forget, let's not lose focus here. This is what I'm looking for. And this is equal to that. But this area is definitely bigger than this area. Right? Definitely. Because we took the minimum value of the function. So this little rectangle here has an area that's smaller than what we have, what we're looking for. Okay? And the other area, which is if I'm taking the biggest value of the function, which is big M. So this is definitely bigger than. Do you see? Do you see it clearly or not? Okay. If it's not clear, I will draw it here. So I'm going to draw the three regions.
Honestly,
Sorry?
you're not including the area between the origin and X, right?
No, not
Okay.
interested in that. Okay, so here are my three areas. I'm going to draw it like this. Okay, the same function 3 times. So this, of course, is what I'm looking for. Okay, and then so I'm just going to go like this. I hope it's clear. So again, this is between x and x plus h, x plus h, x and x plus h. Okay, so the small area is this one. The big area is this one. Is this clear? You understand what I just drew here? This area is definitely smaller than or equal to this area, which is definitely smaller than or equal than this one. Questions?
So the one on the all the way on the left is like when you take into consideration the C, which is the minimum, and then the one all the way on the right is when you like take into consider the max.
Yeah.
But then the one in the middle is just
It's just this f of x plus h minus f of x. Exactly.
okay.
Okay, so just to make sure this is small m, and this, of course, was big M.
Sir,
Good? Yeah.
so it's basically we take the area of the minimum, and that's going to be smaller than the original, and then the maximum is going to be bigger than the original.
Exactly. It's just basic geometry.
Okay.
Good? Let's
Yeah.
okay, let's go a bit further here. Okay. So okay. So what is this area here? Could you tell me what this is? A rectangle. What's the area of this rectangle? Base times height. What is it?
H times M.
Very nice. So m times h. Perfect. This is smaller than or equal to. Okay, so this area we know we said was f of x plus h minus f of x. And this is smaller than or equal to, what's this area? Tell me.
Big M times H.
Yeah, big M times H. All right, so let's take it now up here. So I'm going to rewrite. We're almost done. M of x plus m times h smaller than or equal to big F of x plus h minus big F of x. Still see, right? Oh, did I go too high? Well, you could see. Smaller than or equal to big M times h. Okay, so what I'm going to do is I'm going to divide everything by h now. Divide by h, divide by h, divide by h. So m, small m, smaller than or equal to 1 over h times f of x plus h minus f of x, smaller than or equal to big M. Okay, and the middle term we recognize is very close to a definition of the derivative. The only thing missing is to take the limit as h approaches 0. So that's what I'm going to do. I'm going to take the limit as h approaches 0 on the three sides. So limit as h approaches 0 of m smaller than or equal to the limit as h approaches 0 of f x plus h minus f of x over h smaller than or equal to limit h approaches 0 of big M. Okay, so actually, instead of calling it big M, okay, and small m, so small m we said was f of c. So let's call this f of c. And same thing here, big M, let's call this f of d. How are we doing so far?
So I have a question.
Uh-huh.
I know we're proving formulas, but why is it that the big M has the same H as the small m?
Same H?
Yeah,
This H here?
yeah, that one.
H is the base, because I'm finding, right? If I'm right here,
Yeah,
I'm finding the area of this rectangle. So it's base, which is h, times height, which is m.
okay.
Okay, it's the same here. Also, the base is still h.
So they're all the same.
Yeah, same base, because
Okay.
it's over the same interval.
Okay.
Okay, good. Okay, we're almost done. So what is this?
So
Yeah.
what approaches to 0?
H. H. So I'm making h very, very small. Why?
I don't understand why we do the limit. So
that this here, the middle, becomes big F prime.
oh, okay.
Okay, that's the middle part now.
I swear.
Make sense?
Wait, so by saying that it's F prime, we're saying that it's between the maximum minimum, and that's why that's the function that we choose.
I didn't understand your. Sorry, I didn't understand your question.
I still don't understand why this would be the proof of F. Like, why would F prime be the proof?
I didn't finish yet.
Okay.
You will see. Okay, so what is this here? Okay, so I just want to find what is the limit as h approaches 0 of f of c. Okay, well, c is between x and x plus h. Okay, so basically, if you want, c is between x and x plus h. Okay, so if you take the limit as h approaches 0 of this, this, and this, you will get limit as h approaches 0 of x less than or equal to limit as h approaches 0 of c smaller than limit as h approaches 0 of x plus h. This h is 0, so this is x. This is x, so as h approaches 0, c approaches x.
I'm sorry, sir. Could you repeat that?
Yeah. Okay. So I'm not going to do it for the d because it's the same principle, but the idea is as follows: x plus h, and c is between them. C, right? C is somewhere between them. Now, if I make h very, very close to 0, that means that the space between x and x plus h is almost none. And so c has to get very, very close to x. This is what I'm saying here. Okay, c is between x and x plus h. So if h is very, very close to 0, then c is between x and x. So c has to be x.
Is this the squeeze theorem?
Yeah, that's the squeeze theorem here. Okay, if you want, I write it here. Squeeze theorem. Okay, and so this limit as h approaches 0 of f of c is this actually f of x. And same thing for d. d is also squeezed between x and x plus h. And so this is also f of x. Okay, and so I just showed that f prime, big F prime of x is between f of x and f of x. So I squeezed it also, so it has to be f of x. So big F prime of x is equal to f of x, and that completes the proof. Okay, that's also a squeeze theorem. So fundamental theorem of calculus 2 proof. Okay, so so I'm just going to remind you what it is. Okay, it's that the okay, so the integral from a to b, the area from a to b of f of x dx is equal to big F of b minus big F of a okay, where, of course, big F is an antiderivative of small f. Okay, so to improve. Okay, so it's very simple. So let's call big G of x is the area from A to x of f of t dt. Okay. And big F be an antiderivative of small f. Okay, so G is the area and big F is the antiderivative. So first thing, big F prime, since big F is an antiderivative of F, so F prime is actually small f. That's what it means. True. And by the fundamental theorem of calculus part 1, we know that the derivative of this is also f. Okay, so this we just proved. FTC1. Okay, so big F prime and big G prime are both equal to small f. Want me to repeat this?
Yes, please.
Okay, so again, so big G, what is big G? It's the area from A to x. Okay, it's not an antiderivative. I don't know. It's the area from A to x. And let's say I have a function f, big F, which is the antiderivative of f. Okay, so just like we did at the beginning of the course, finding the antiderivative of a function. Okay, so let's say if this was cosine, this would be sine. Okay, the antiderivative. Okay, so the fact that big F is the antiderivative of small f means that if I derive big F, I will get small f. That's one thing for sure. That's what it means that f is the antiderivative. Okay? And second thing is that by the part 1 that we just showed a few minutes ago, we just said that if we do the derivative of the area, we're going to get the function. So if I do the derivative of big G, I will get the function as well. So both derivatives of these two functions are small f. Is this okay?
Okay, I have a question. So G has to be considered as an area first before being considered as an antiderivative?
Exactly. Exactly.
Okay.
It's an area, and if I derive the area, I get the function. That's what I showed in part 1. Okay, so what does it mean that f and g, if you derive them, you get f? Well, it means that let's say f is cosine, let's say f is cosine, then f could be sine plus 1, and g could be sine plus 5. They both have the same derivative of cosine. Okay, so basically they're just off by a constant. F and g are off by a constant because they have the same derivative. So I'm going to write this. G of x is equal to f of x. Should I do the opposite? F of x plus c. Let's go like this. Okay, almost done.
Wait, so can you repeat the last part? Like the g of x equal f of x plus c?
The last part, this here?
Yeah. Yeah.
So here you okay?
Yeah.
Okay. So what I'm saying is that these two f and g, they have the same derivative. Okay. So take two functions that have the same derivative. Okay. Let's say you had sine x, so that's f of x, and g of x. Sorry. I want to go fast and I'm not making it clean. So 2 seconds. So let's say big F is equal to sine x and g of x is equal to sine x. So let's say this is plus 5 and this is plus 2. Okay, so or just sine. Here you go. So if you do both derivatives, f prime and g prime, they're both equal to cos. You understand?
Yeah.
That's why f and g are only off by a constant. Because when I'm going to derive it, the constant will cancel.
Okay, so in that case, g of x would equal f of x minus 5?
G of x, yeah, exactly.
Okay.
Okay, they're just off by a constant. That's what I'm saying. Okay, so now we're almost done. Once this is clear, that f and g are off by constants.
Sir, I have a question.
Sure.
Why wouldn't it be g of x plus a constant equals to f of x?
Same thing.
Oh, it's the same thing?
Same thing. Plus, minus, who cares? The constant
Okay.
could put there, who cares? Okay?
Okay.
All right. So basically what we have, g of x which is equal to the area from a to x of f of t dt. Okay, so what's g of b? So g of b is the area from a to b. You know what? 1 second. I'm going to do it something better. I'm going to do it a bit better. No, let's do it like this. F of t dt, and g of a is the area from a to a, f of t dt. You with me? Okay, I'm just replacing the x by b, and then replacing the x by a. So g of b minus g of a is this area minus this area, which is just the area from a to b, f of t dt. Okay, but g of b we said was f of b plus c minus g of a, which will be f of a plus c, cross out the c's, and there you go. You will have the area from a to b, f of t dt is equal to f of b minus f of a. Okay, f being the antiderivative.
Sir, how did you go from the second to last step to now? So like, how do you go from g of a times, well, the whole thing right here, yeah,
From here to here,
to, yeah.
I'm just replacing, since we know that g of x is f of x plus c.
Oh, so you're just replacing g of x by all that?
I'm replacing the x by b. Yeah.
Okay,
Exactly.
okay. Thank you.